All right. So, last one more time. Everybody's got me, right? Nope. Everybody's got me, right? Cool. All right. So,
Yep.
talking load calcs. First things first. I want you guys to, if you don't have your manual J8 available, get it available as soon as you can. You should probably start reading through it. I'm not gonna actually teach out of the book that much. I'm gonna try and teach most of this without utilizing the book a ton, except for when we got to get to tables and things like that. But you'll still need it. What I would probably do is start reading through. Well, just start on section 2. Start on section 2. Read through that a little bit. And then kind of move on from there as you can. As we talk about this stuff, we'll be talking about stuff through basically all of the first, basically from section 2 through section 6 is what we're going to basically be covering all at once. And then we'll start looking at the examples and actually doing some block loads, and then we'll talk about room loads. But before we get into that, there's a lot of basics we got to cover to make sure you know what we're doing and what we're looking at. So I'm going to try, this is going to be a little bit different, but I'm going to try teaching basically mostly out of using WriteSoft for examples and going through actually using the speed sheets this year. So I'm going to post this speed sheet on I'm going to post this speed sheet on Google Classroom, and what we'll do is we'll probably fill out some doors, glass, walls, ceilings, and all that stuff. That way we can utilize them in some examples. But to use this, you got to fill some stuff out. So we'll talk about that a little bit later, but we'll see if we can use these together. Now, the caveat with that is, especially if we're going to try and use them together, I don't know. I guess I can try. I can see if this will work on Google Sheets, but maybe in the group text I'll ask. But it would be ideal if a lot of you guys have access to Excel. If that's going to be a huge issue, maybe we can just go back to basically I make a simpler form of the speed sheet that you can print and fill in by hand. That's typically what I would do every year. But if we can mostly use Excel, then we can maybe get some stuff in a little bit quicker. So we can talk about that in the group text, like I said. But that would be neat if we could do that, because that's the actual sheet you would use for load calculations. So, quick overview, real quick. The quick overview is we're going to be talking about how to do residential load calculations using the book you guys have, which is Manual J8 AE, the abridged edition. The abridged edition is only allowed in Virginia under particular circumstances to be used for load calculations. Those circumstances are primarily additions where less than 50% of the house is being upgraded. Okay? Any other load calculation you need to do out in the real world has to be done on a program like what you see up on my screen, which is WriteSoft. I don't have any particular links to WriteSoft or anything like that, but I will tell you, out of the load calculation softwares that I've used and seen, it's the easiest to use and mess with. It's not cheap, but it's the easiest one if you're going to actually do load calculations to work with. If you get their duct design stuff, it's very easy to do manual J, S, and D all in the same program. Okay. There are other options that are less expensive that are available for you to use, but they have their pitfalls. Brightsoft has its pitfalls too, don't get me wrong. I don't think they have updated the use of this program for 15 years. Swear to God, they've done nothing to update anything.
Why do we need a manual J?
You need a manual J. So, we haven't got that far yet, right? But technically, you should be doing a manual J, at least a block load, every time you change out a system. Most people don't do that as long as they're going to change, as long as they're going to put a system in that is equal to what was existing before, they will not do a manual J load calc. But ACCA recommends a manual J load calculation anytime a system is changed. The reason for that is if they upgraded Windows or they upgraded installation or they added any, any additions or anything like that since the last time a load calculation was done, then the new system you install will not be the correct size. So technically, anytime you're installing a system in a house, you should do a manual J load calculation, whether it be a new one or a replacement. Real world talking, you need to do a manual J anytime you're pulling a permit to install a new system in a house or an addition. So in Virginia, pretty much every jurisdiction requires that if you are, if somebody's doing an addition on the house or they're doing a major remodel, if you're pulling a mechanical permit, they're going to also require that somebody do a load calculation. And even in those rare instances where, say, the homeowner is handling the installation of the system themselves or something weird like that, every once in a while you run across that. It's a little bit less common than it is in plumbing or electrical, but it still happens. When they do that, they still need a licensed contractor to do a load calculation because you have to be able to sign off as a master tradesman on the load calculation. So basically anytime a house is being remodeled and a mechanical permit is being pulled to condition certain spaces, or it's being a new house is being built, you will have to be able to do a load calculation. And then you'll have to be able to provide a drawing on how the duct is supposed to be installed. I will tell you guys that they make it exceedingly easy to get this paperwork through. Your load calculation does not have to be right, okay? It does not have to be a very good load calculation. They're going to double check some things, but they're not going to double check enough to make sure that you did a good job. So it is very important that if you're doing these things, that you understand what you're doing as good as you can, and that you follow the rules as best you can. Because again, just because it gets through plan review doesn't mean it did a good job. Just because somebody had the software and used the right software does not mean that you did a good job. So it's one of those things that they require, but really what they're doing when they make you do those load calculations is they're trying to put the burden on you so that if that homeowner comes back later and says that this system doesn't work right or they're having this and that problems or something's going wrong.
Your microphone is on. It's disturbing.
What?
I think,
Okay.
Mario microphone is on, so that.
Gotcha.
Disturbing. I didn't hear anything.
Okay. So anyway, again, as you do this load calculation, it does not guarantee that anything is correct. All right. And what the county is basically trying to do is put the burden on you. They're trying to say, if that homeowner has any issues, they're going to go back and say, this person or this contractor did this load calculation. They are supposed to be qualified to do it. If it was not done correctly, then go back to them with any problems you got. So that's just something to keep in mind. The liability essentially ends up falling on you to make sure that you did a good job. Now, if for any of you guys who've done residential construction, when you're doing like subdivisions and things like that, a lot of times that'll be designed by an engineer or something like that. So if there's a bunch of the same house being built, or it's getting built by a large housing contractor or something like that, it's usually going to end up, they're going to have a set of drawings for those. But if you're doing like single one-off custom homes and things like that, that's where you need a load calculation. And there's not that many guys out there that can do one. Okay, so it's not a bad thing to be able to do. If you learn how to do them and do them well, you can generally at least make your money back on the software within a year. And then after that, it's just doing the work and, charging fees for them or doing them for yourself or whatever the case is. So it's not a bad thing to get into, but it does take a reasonable amount of work. After we're done with this class, I would not say that you guys will be 100% qualified to do it. I would recommend you take some more classes on your own, maybe take a class on the software that you're going to be using, things like that. But you should be well ahead of somebody who obviously hasn't gone through the steps in this class to do it. We will be going through Manual J8 AE, right? The abridged edition. We won't go through the full Manual J8, but we'll go through 8 AE. If you understand J8 AE pretty well, you're in good shape to understand regular Manual J8 just fine, okay? But that would be a purchase you should make, is buy the actual full Manual J8 for yourself at some point. Then we will talk about Manual S, which is selecting equipment. Then we will talk about Manual T, which is placement of diffusers. And then we will talk about Manual D, which is sizing ductwork. J and D take the longest. Manual S and T are usually only a couple classes each. So those don't take long at all. You guys only have Manual J. You do not get copies of these other manuals I just mentioned. But I will try to give you enough information from those manuals that you understand everything that's going on. And if you want to purchase those for yourself to actually read through them, you can do so. But especially Manual S and Manual T, you'll have a full primer on those for the most part. And then Manual D is the only one I highly recommend you get. If anything, I think Manual D is the most important. Understanding Manual D will help you in almost any aspect of the trade that you're in if you do anything that has any ductwork involved. Even commercial, Manual D helps you understand what's going on in the commercial sizing of a duct a little bit. If you understand Manual D, you kind of get an understanding of what an engineer is doing when they're sizing commercial duct. But we got to go through J and understand it before you can really get to Manual D and understand it well. So for those of you who will never pick up anything on load calculations again, some of this information may be less useful for you on a day-to-day basis, but all the concepts are very useful to understanding situations. Understanding where heat comes in, how it comes in, and how to mitigate it is important in every aspect, not just designing residential homes. But in general, if you get your master's license as a master mechanical contractor, it's generally only going to be residential that you design a lot when it comes to mechanical. That being said, there are instances where there are small commercial spaces that you can design as a master mechanical contractor as well. I'll pull up a table on that when we learn about our journeyman stuff. Understanding what you can do as a journeyman / a master is an important thing to understand. So there are instances generally under 100 people in a space, under 3 stories or less, you can design a commercial space. These concepts are the same for commercial spaces, but we don't use the same software. There is a commercial add-on for RightSoft, and there are applications that are specific to commercial. The problem with commercial is a lot of times there's a lot more glass and things like that will affect the load calculation, and there's a lot more people involved that affect the load calculation, and a Manual J load is not really set up to take those situations into account. You are going to Manual N or something of that nature, or an ASHRAE standard for commercial load calculations. Okay, so everything we'll be learning is core concepts across the board, but it's specifically applicable to residential load design. All right, it's not meant to be transferred. You can't take manual J and design your nail salon down the street because you need to put a new RTU in there. It's not how it really works. All right. So again, to reiterate, we're going to first be talking about manual J. These are all ACCA standards, by the way. ACCA basically makes all the standards for residential load calculations and residential design. So maybe actually I can pull this up. Do I have? Yeah, I should have Edge. I'm gonna pull. Do I not? Oh, someone's coming in. Is it worth it? I don't think it's worth it. We'll do it. We'll do it some other time. But anyway, I'll next class I'll pull up ACCA's storefront and we'll look at all of ACCA's books. There's a lot of books that are good to look at on ACCA. There's stuff outside these four that I'm going to talk about. But when it comes to designing systems, again, Manual J is your load calculations. 8th edition is the current edition. Manual T is diffuser placement. I don't think that manual has changed since the 70s or 80s, but it's still just as relevant then or now as it was then. Then you have Manual S, which is equipment selection. And you need to finish a Manual J before you can use Manual S. And then Manual D is duct design. We will go through those basically in that order. Or Manual S and Manual T, I always swap back and forth. So, is there any questions on what I've said so far?
Nope, all good.
All right. So, first thing to understand is block loads versus room by room loads. So first we'll be doing block loads. Block loads are the simplest load calculation. A block load is what you should do on every equipment change out. Okay. Again, the only time it's required by the state of Virginia is when you're doing an addition or when you're doing an addition or a new home. Okay. But ACCA recommends them on every equipment change out. So, in general, in those instances, you only need a block load. A block load tells you the load for the entire house and the entire house only. You can't split it up room by room, as opposed to a room by room load. Really, the only time you need a room by room load is if you're going to design the ducts going to into each individual room. So if you need to know how many CFM the master bedroom needs, you're going to have to do a room by room load. If you only need to know, do I need a 2-ton or a 3-ton system, you're going to do a block load. The loads only come from the outside for the most part. The only internal loads are appliances and people. Internal loads are only cooling loads. You do not get heating loads. You do not get heat loss from anything within the structure. You only get heat gain from things within the structure. So, what I mean by that is I drew a perfectly square house with 9 rooms right here, right? Make sure I got you. I don't have you on the right page. Hold on.
Yes, it's getting ready to see.
Yep.
You can't see it.
Yep, you can't see nothing. All right, now you can see something. So I'm in RightSoft right now, all right? What we have here is we have a house with 3 floors, all right? Just as long as you can see the squares, you're good, all right? You got a house with 3 floors, basement, well, not even a basement, just call it a first floor, a second floor, and a third floor. And they got 9 perfectly square rooms on every floor. So, if we start on this first floor, right, 1, 2, 3, 4, 5, 6, 7, 8, 9 rooms with the front door facing, this would be a front door facing south. If you guys can see the compass up top, I think you can. Yeah, you got the compass up top here. So that compass is facing north. This front door right here would face south. This room, right? And we'll go ahead and start drawing some windows in here while I'm talking. This room has 2 walls. Okay? This room has 2 walls because there's only 2 walls. That thick line is the outside wall. That outside wall is the only wall when it comes to a load calculation. The inside walls are partitions, right? The inside walls separate rooms from other rooms. But the walls are any wall exposed to the outside. And any wall exposed to the outside is going to have heat gain and heat loss. Because if it's colder outside than it is inside, then the heat is going to want to travel from greater concentration to lesser concentration. So if it's warmer inside, the heat is going to try and escape. If it's warmer outside, the heat is going to try and get in. Okay? So we have heat loss and heat gain. Heat loss is when the heat from inside goes to the outside in the winter. Heat gain is when the heat goes from outside to inside in the summer. Notice we don't, if you go back to our first class, notice we don't talk anything about lost cooling. Okay, we don't lose cold. Cold does not get lost. Cold is the absence of heat. We only lose heat or we gain heat. And that'll help you understand things as we keep going. So this room up here in the top left, right, has 2 walls and it has 2 windows. This room right here has 1 wall, right? And then this corner room, again, has 2 walls. So, when we get to the second floor, all right, so all these rooms experience heat loss and heat gain. Well, no, let's talk about this middle room right here first. Okay, so on the first floor, this middle room has no walls, right? But it's the first floor of the structure. So this room will have no walls. It has no ceilings because there's a floor above this, right? So we have, again, first floor, second floor, third floor. This room in the middle on this floor has no ceiling because the ceiling isn't exposed to the outside, but it does have a floor, whether it be a slab on grade or it be over a crawl space. There's a floor here potentially, right? It gets more complicated on slabs, but just bear with me for now. This room has a floor where you could lose heat through the ground, basically, right? Or to the outside through the crawl space. But it's got no walls. When you get to the second floor, same thing. This corner room, we've got 2 walls. Then the next room is 1 wall. The next room has 2 walls. This room has 1 wall. Next room has no walls. Next room has 1 wall, 2 walls, 1 wall and a door, and then 2 walls, all right? This middle room in this case, all right, this middle room on this floor has no floors or no ceilings because none of it's exposed to the outside. So this room cannot have any heat loss or any heat gain except for the people in it. If this was a living room, we would add an allowance for people and appliances, and those people and appliances would provide heat gain. But there would never be any heat loss in this middle room on the middle floor. And then when we get to the next floor, we have walls, ceilings, and all that. Okay? So the point is that we're only dealing with heat gain and heat loss to the outside. So if if the part of the room does not communicate with the outside, that is not a structural element that you need to worry about in a block load. The only structural elements you need to worry about in a block load are the ones that heat can travel through. We're going to talk about all those ones individually, but I want to make sure that you understand that heat loss and heat, we only lose heat or gain heat, and it's only to the outside, except people and appliances create heat inside a house. So typically each person, just to jump ahead, and they actually changed this number, so I might get this wrong. If I get this wrong, we'll fix it later, okay? I'll make sure I teach you right later. But it used to be, as long as I'm not messing up my numbers, because it changed from J7 and J8, and I always used to teach J8. And I don't have to look at the sheet that often to double check myself. No, let's pull it up. Should be 300 sensible BTUs per person. Let me see if I can pull it up in RightSoft. All right, so if we got this room, internal loads, bring it up. Occupants, no, it's 230 now. It used to be 300 per person. Now sensible loads per person are 230 BTUs, and latent loads per person is 200 BTUs. So people provide both sensible and latent load, okay? You actually lose moisture by breathing and perspiring and everything else. So you actually do create latent load in a building. You have sensible load from people and latent load from people, and then you have sensible loads from appliances. All right. So with that in mind, I don't think your book has it. The other thing that was interesting that we used to talk about every year that I don't talk about as much since we switched to using J8 is the different types of heat movement, right? You have convection, radiation, and conduction, okay? And most of the heat lost is through conduction, from heat just being conducted to the inside and outside. But you have radiative loads, right, from the sun, and then you have heat moving through convection, which the best way to think about that is boiler systems with radiators and stuff. Those are actually convectors. So there's a good Google assignment for you. Look up, if you can't remember them from science class in high school, all right, look up conduction, convection, and radiation, and heat loss through all those means, or heat gain through all those means. Remember, the most important law of thermodynamics is that heat always travels from greater concentration or lesser concentration, or you can think of it as heat always tries to seek equilibrium. So again, if it's warm in the house, the heat is going to try and escape the house to warm up the outside. If it's warmer outside than in the house, the heat is going to try and get into the house until it's the same temperature as the outside. And we have to mitigate that. Our goal with the load calculation is to be able to maintain a temperature as fast as we are gaining or losing that heat. So, with that said, I want to pull up this speed sheet real quick, and we're going to talk about the things you need to know. So, if we're trying to, what we're trying to do, right? The overall goal of this is to determine how much heat is lost or gained on a design day. A design day is not the worst case scenario, okay? A design day is kind of, think of it as the average worst case. So if we get 100-degree days in Virginia, they're not very common, right? It's not very common that we'll get a 100-degree day, even though we get one now and then. But we are relatively likely to get a 95-degree day a good amount in the summer, right? So 95 degrees is what we tend to design to in Virginia outside in the summer. So I'm going to change this. I'm actually going to fill out part of this speed sheet for you so that you guys have it partially filled out with some of this information in it. So we're going to do Virginia, and let's see if they have it. Fort Belvoir. It's close. It's not quite right. Did they get another one? Fredericksburg. Fredericksburg is closer, but no, it's not quite. Fort Belvoir would be right. We'll pick, I'm trying to see if they got one that has Fairfax's required design conditions. And really, Fort Belvoir should. So, it's actually 17. So, the important thing to remember here is that we're always going to be designing for a certain temperature difference inside and outside. So to know what the temperature difference is, we have to know what the design conditions are, okay? And this is the first thing I want you guys to remember. I'm going to repeat this multiple times, and you should be able to call it back to me very quickly. One of the first things to understand is the design conditions for this area. And this class is based out of Fairfax County. And if you do a load calculation in Fairfax County, you're going to be designing at 70 degrees. I'm going to go ahead and try and make this bigger too. You guys see that pretty... Oh no, I'm still on the wrong sheet. I'm sorry. Thought I switched. All right, here we go. This is our speed sheet, okay? So this is our ACA speed sheet, and we're going to put our design conditions in here so you can see them. All right, so this is an overall view of it. If we're doing a block load, we really only need this section of it. But if we're doing work in Fairfax, Virginia, and we're doing a load calculation, we need to know the design conditions. The design conditions are 70 inside 70 degrees in heating. In cooling, we design for 75 degrees inside. The indoor design humidity is 50%. Outdoor in the winter, we design for 17 degrees. Outside in the summer, we design for 95 degrees. And the grains difference, which is the humidity difference between inside and outside, is 46 grains of difference. All right, so I want you guys to know that like the back of your hand. First rule is number one, when we design for heating and cooling, inside conditions are always 75 in the summer and 70 in the winter. Always, 100% of the time. You never change those numbers at all. Every proper load calculation will be designed at 75 in the summer and 70 in the winter. I don't care if they want it set to 72, you don't design the load calc for 72. I don't care if they want it set for 70 in the summer, you don't change the load calc for 70 in the summer. It's 75 inside in the summer and 70 inside in the winter. Okay? Remember it. You do not change those numbers because, as another quick aside, when we do our load calculations, we are using a somewhat simplified method of doing a load calculation. We are not doing it exactly to a T. Our numbers do not have to be 100% exact. I do not need to know that there is 25.67 square foot of windows. I only need to know that we have 25 or 26 square foot of windows. We're going to be as close as possible without worrying about every little number. All right? But if you go changing numbers and you go fudging them, then you're going to mess everything up. And if you read through your book, see if I can find it real fast. If you read through their book, your do's and don'ts of load calculations on making accurate load estimates and things like that, one of the don'ts is don't add any padding Manual J, making an accurate load estimate. Don't use for any type of commercial application. Don't use for large multifamily dwellings. Don't design for record-breaking or news-making weather conditions. Do not add a safety factor. Do not design for abnormally low or high indoor temperatures. Do not assume there will be no internal shade, so on and so forth. You do not make changes to how you do the load calculation, because if you do, it won't be right. So if it looks messed up, double check you did everything right. Don't add any safety factors, and don't change the indoor design conditions. I will tell you that most of the studies that I have read indicate that oversizing a cooling system is not nearly as detrimental as they will say, but I will tell you that most of the time you're going to end up with a slightly oversized design anyway. So you don't need to add any safety factor for it. If you do everything right, the system's going to be oversized for 98% of the conditions it's going to see. So there's really no reason to add any safety factor. By the time you pick your system, you'll have added a safety factor, because usually you're going to need like a 2.1 ton system, and you're going to have to put a 2.5 ton in. Or you're going to need a 2.6 ton system, and you're going to have to put a 3 ton in. So there's no reason to change these conditions. Again, indoor design temperature in the winter is 70 degrees. Indoor design temperature in the summer is 75 degrees. Outdoor design condition in the winter for the purposes of this class is 17 degrees. Outdoor design conditions in the summer for the purposes of this class is 95 degrees. Now, if you go somewhere else in Virginia, this may change. So if we design for Norfolk, no, Norfolk's the same except for humidity. See if I can find somewhere in Virginia that's different. What about Danville? No. Or is it because I changed it? Is it because I changed that?
Winchester.
Yeah, no, I think because I changed the number, now it won't update. Yeah. See if I can get it to change automatically again. So I guess that's a lesson we just learned on this speed sheet. You go messing with these numbers to input what it should be, and it won't change it for you automatically. So anyway, Fredericksburg, for instance, is 14 and 95. If we go to somewhere, let's just go to a completely different state. If we were designing systems in, I don't know, Connecticut. We're designing systems in Connecticut, in Hartford. Okay, it's 6 degrees outside. And I guess I changed the 95 too, so that's not changing. I'm sure it's not 95. It's one nice thing about using software instead of these speed sheets. So Connecticut, in Hartford, Connecticut, it's 88 in the summer and 6 in the winter. All right. So obviously these outdoor design conditions change for different areas. You know, if we were in, let's try a place that should probably be hotter. Let's try something like New Mexico. If we're in New Mexico, in Albuquerque, oh, it's 18 in the winter and 93 in the summer. I expected that to be a bit different. Anyway, point is that depending on where you are, all these numbers change, right? Outdoor design in Georgia and Brunswick is 34 in the winter. So these outdoor design conditions are going to change where you are. So those numbers can change. The indoor design condition never changes. So if I ask what the indoor design conditions are, those numbers will never change. If I ask you what your outside design conditions are, you should know what they are for our area, but the best thing to do is if you're doing a load calculation is to ask the authority for which you're doing the load calculation, right? So if you're in Fairfax County and you're not sure what design conditions are supposed to be, you call Fairfax Permitting and say, what are my design conditions supposed to be for a load calculation? And they'll tell you, because that is one of the things that they'll check. If you're in Richmond, you call Richmond's permit office or plan review, and you say, what's the design conditions supposed to be here? All right. That's the best way to find outside design conditions, but inside design conditions are the same across the country. And you also need to know the grains of difference. That's for calculating humidity. And we always do indoor 50%. You can do indoor 55%, but generally we do indoor 50%. Okay. So, is there any questions on any of that? So what I want to talk about next, well, before I talk about that, let's talk about temperature difference, right? So if we're designing for 70 degrees inside and heating, and outside it's 17 degrees, our heating temperature difference is going to be 53. If we design 75 inside cooling, 95 outside cooling, our cooling temperature difference is going to be 20. So 53 degrees is our heating temperature difference. At 53 degrees, what that means is whatever the U value is, we're going to talk about U values soon, but a U value is the amount of heat that goes through a surface per square foot, basically. All right, per whatever. Think about it as per square foot, because we're going to talk about HTMs, but the U value is the amount of heat that transfers through something, right? So, well, if we have an HTM or a U value of 1, that means that for every degree temperature difference, we'll lose 1 BTU. So, if we have 53 degrees temperature difference, that means we're going to lose 53 degrees through that surface. And that's what we want to get to. We want to get to the point where we know how many BTUs we lose based on our temperature difference. But the temperature difference is always going to affect that. Because the bigger the temperature difference, the faster the heat moves. Because heat's trying to seek equilibrium, right? So the bigger the temperature difference, the faster heat moves. That's all I'm trying to get at here without getting too deep in everything else yet, because we still have a lot of concepts to explain. But the heating and cooling temperature difference are the most important numbers. The only way we can get those is if we know the indoor design and the outdoor design. But really, the only reason we get those is so we have the heating temperature difference and the cooling temperature difference, so we can calculate BTUs lost. So again, these numbers for the purposes of this class, all right, for the purposes of this class, these numbers are never going to change in our examples. I always keep them the same the whole year so that we don't get confused by something as simple as the temperature difference. You guys need to know how to find it and figure it out. But I don't want to get bogged down with playing around with temperature differences just so we can see different numbers. For the purposes of this class, everything we do in load calculations is going to be an indoor design of 70 in heating, an indoor design of 75 in cooling, an outdoor design of 17 in the winter in heating, an outdoor design of 95 in summer in cooling, a heating temperature difference of 53, a cooling temperature difference of 20. You should know that that heating temperature difference is calculated by the indoor minus the outdoor temperature and heating. And then that cooling temperature difference is the outdoor minus the indoor in cooling. The grains of difference will always be 46. and you get this grains of difference the same way you get these other numbers, by pulling up a chart from ACCA. And this one, they actually don't change very much. So no matter whatever ACCA says this number should be for your city is what the number should be. Whereas these design temps, for some reason, counties tend to change them, but only by like a degree or two. But this grains of difference will always be 46. The daily range, this is the next number on here that you have to have. The daily range is the difference between the daytime temperature and the nighttime temperature. So, for instance, if you were in a desert, right? If you were in a desert, deserts are really, really hot in the day, right? And really, really cold at night. So it's going to have a high daily range. Whereas, if you're in the middle of a rainforest, you're going to have a low daily range because it tends to be the same temperature all day long. For most of our climates, we're going to have a medium daily range. But in your book, as a matter of fact, what pages are in your book? In your book, there's tables. You should find table 1. Table 1 in your book starts on page 105. Actually, I think there's an explanation on it. Yeah, it starts on 103. Yeah, all your tables start at page 101 in your manual J8. Okay? So most of where we're going to be looking for this class, which you're going to use your book for the most, basically starts 100 pages in. We're going to be talking about everything on the first 100 pages kind of as we learn these things. But you really need to be able to start at page 100. So, as well as starting to read the first 100 pages of this book in your own time as much as you can, if you look at table 1A starting on page 105, you'll see all these numbers for each individual area. And again, for the purposes of this class, we will never use this table. But if you need to know the design conditions for a specific area, then what you're supposed to do is go through this table and find the area closest to you. So again, if we go to Virginia, you can pull out your book if you want and follow me, but I'm just going to tell you. If you go to Virginia, which starts on page 129, you find the city in Virginia the closest to where you're doing your load calculation. So again, if we were in Fairfax County, we're probably talking Fort Belvoir or something like that. So Fort Belvoir, Newington, unless there's another city closer to you, would be the one you would look at if you're using ACCA's book. You have the elevation here, you have latitude. Heating 99% outdoor dry bulb is your outdoor design condition and heating. So according to this book, it's 18 degrees. For Fairfax County, they require 17, but you're within 1 degree. If you designed it at 18 degrees outside, that would be fine. The outdoor air design condition and cooling is the next number, the 1% dry bulb. Our 1% dry bulb is 93. Again, Fairfax requires we use 95, but 93 is within 2 degrees. It's probably more accurate, honestly, but we design at 95. Then you have the coincident wet bulb, which is irrelevant. Just ignore it. You have 55% indoor design grains. Ignore it. The next one is 50% relative humidity indoors. You design for that. That would be your grains difference. That's 37 is what you would use if you're going by ACCA's conditions. We use, what do we use? We use 46, right? Yeah, 46. So actually, they're designing closer to 45% indoors. They're designing to closer to 45% indoors. Like I said, you can pick any one of these three. Just understand that the design grains you choose, the latent heat load you pick, is going to be what the humidity is inside. So if you design at 55%, it's going to be more humid inside than if you were to design at 45%. So most people design for as much latent load as possible, and we'll talk about that more as you've picked fan speed. And then if you keep going, you see all the M's. That's a medium daily range. The only place on this sheet that has a low daily range is Chesapeake. Everybody else has a medium daily range in Virginia. There's a couple more in here, but most of our areas are medium daily range. And then the HDD and the CDD ratio, you could basically ignore it. It's not important. Your most important numbers are your 1% dry bulb outdoor, your 99% dry bulb outdoor and heating, your design grains at 50 or 45%, and your daily range. If you're in doubt, use whatever is in the software that you're using, because hopefully you're using software for this most of the time. I've never actually used this speed sheet we're going to look at, okay? So this will be fun for us together, but I do generally teach using a simplified version of this sheet, so there's not as much stuff here to look at. It's not much more simple than what they already have here, but generally I try and do it a little simpler. So that's where you get all of these numbers so that you remember. Remember, if you need these numbers, you should be looking at Table 1 and your Manual J. But the real way to get these numbers most of the time, especially if you're doing work in the state of Virginia or the surrounding areas, is to always have 70 inside in heating, 75 inside in cooling, design humidity, cooling, relative humidity 50%, right? And then ask the code official, someone in plan review or in permits, what your outdoor conditions should be to pass plan review in that jurisdiction. And then the ACF here, this is a correction factor, altitude correction factor. Unless you're way up in the mountains, that's always 1. So you should, if you're in the mountains, you'll have to change this number because BTUs change based on the density of the air, right? So the less dense the air gets, you'll have an altitude correction factor for these numbers. But for us, it's generally 1. It's pretty rare that you do something high enough in the mountains that you have an altitude correction factor. Just remember that it's there if you ever start working, in Denver or something. All right. So those are the design conditions that we need to do a load calculation. One more time, these numbers will never change for the purposes of examples. So when I upload this speed sheet that I've already started modifying onto Google Classroom, you can look at these numbers and just always use the same numbers. But you should know that you get them at a table 1A in the book if you've got to do it in the real world, or call the local code official. Hopefully I've repeated that enough that you guys are banging your head against the wall and you don't forget it. Because I will ask questions on every single one of those, and it drives me nuts when they're wrong. Because I try and repeat it so many times, it's annoying. All right. Besides the design temperature differences, so we can know how many BTUs are lost, we need to know what everything in the house is made of that communicates to the outside. Okay? So we'll have windows and glass doors, skylights, if there's any skylights. We need to know what the wood and metal doors are made of. We need to know what the above grade walls are made of. You can generally ignore partition walls, but we'll talk about those when we get to the tables. What the below grade walls are made out of, if there's any walls that are underground a little bit, basement walls. Ceilings Again, partition ceilings are pretty rare, but you may need those. I usually don't include partition walls and partition ceilings. Passive floors or exposed floors. All right. So what we're talking about here is crawl spaces versus slab on grade. And then everything else is later. The only thing I want to be able to discuss on how to get it first is windows and glass doors and all that stuff. So I want to talk about this a little bit, each one of these things. But to do that, I want to go back to RightSoft. And the reason I want to do that is because I want you guys to get a visual of all these things we're going to talk about. So I guess this is the most important thing first. Before we get into it, we'll talk about something. Windows are the most important, so let's talk about Windows once first. All right, let me ask you guys a question, because I think I already know the answer, but it's starting to get important that you guys can read this. Oh, it doesn't show the window. Okay, hold on. Let me see if I can get this pulled up. Here we go. No. 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 This is really annoying. All right. See if I can make this readable. If this doesn't work, we're just going to share the screen, which is probably what we're going to end up doing anyway. Because at this point, I want to make sure you can read this stuff. Can you guys read what's on my screen? Kind of, sort of, not really. Okay, let's try this. Does this help? Can you read what's on my screen?
Yes.
Okay. All right. So let me just make sure you guys can see the house again or not, right? Very simple house, right? But you guys can see the house. And if I click on this screen, you guys can see that. And let me see if OBS is bringing it back up still. So if I do this, if I close this, OBS should go back to normal. Okay, good enough. This should work. Okay. So what I want to do is I want to talk about each one of these things independently. We need to know all the parts of the house that communicate with the outside. So the biggest factor when it comes to load calculations is windows, right? You lose and gain a lot of heat through glass. So we'll talk about windows first. But first, guys, give me like 2 seconds. Give me 2 seconds, and then we're going to talk about windows. All right. So when we do a load calculation, windows are the most important factor. So when we talk about doing a load calculation on an existing home, one of the most common questions I'll get is, how do we know what's in all the walls? How do we know what's in all the ceilings, right? Because you didn't build the house. You don't know how much insulation you have. You don't know. Sometimes it's hard to figure out how much insulation's in the attic, or how much is in the walls, or, maybe the entire construction of the wall if it's been remodeled a couple times, things like that. It can be hard information to find. What you need to do is get as accurate as you can with every building element, starting with the most important ones. And the most important one, by far, is your windows, because you lose and gain the most heat through your windows. We lose so much heat through our windows that is extremely important. When we talk about manual T, you'll find that we tend to put diffusers right next to windows. The reason we put our diffusers right next to windows is to mitigate the heat loss through those windows. We call them draft barriers. And you can actually buy, if you guys have ever done commercial work, you can buy little units called draft barriers. And they're little electric heaters that you put underneath of windows. Most people think that they feel a draft through a window because the windows aren't sealed and they can feel the air coming in the window. Although that does happen, that's usually not true. What's usually happening is you're feeling the heat rush towards the window to get out of the house. And it actually creates air movement, and you can feel that air movement of that heat escaping through the window. Okay? So, windows are our most important thing. We need to know what the windows are made out of. So when you're doing a manual J, the things you'll need to know about a window is it a single pane window? Is it a double pane window? Or is it a triple pane window? You can usually visually figure this out by looking at the window. Do you see one pane in it? Do you see two panes in it? Or do you see three panes in it? If you look at how the window is constructed, you can usually see the most common ones are double pane windows, and you can usually see the single pane of glass on one side and the single pane of glass on the other side. If it's a triple pane, you'll see another notch in the middle where the third pane sits in the middle of the other two windows. If it's a very old window, it'll be a single pane window. Triple panes are pretty rare, but on a very energy efficient house, you may see a triple pane window. You need to know the type of window it is. Is it an operable window? Is it a fixed window? Is it a sliding glass door, a French door, or a styling glass rail, a rail glass door? Really, the most important thing here is operable and fixed windows, because fixed windows don't have, we don't call there being as much infiltration from the outside through a fixed window, because it's completely sealed and it never opens. You don't get any air actually escaping in and out of a fixed window as much as an operable window. When you actually do load calculations, what you'll find is these door types are basically the same as an operable window. So really, if you never pick these, as long as you get the size of it right and call those doors operable windows, it'll be fine. But notice that we have doors and windows. Anytime over 50% of the door is glass, it is not a door. It is a window. Okay? So when we're talking about windows, or if you want to learn a fancy word tonight, fenestration. Fenestration is a nice fancy word for windows that you'll see, like what is it called? See if I can find this. It's like the National Fenestration something. Oh, I'm not going to remember it. It's going to drive me nuts. There's a rating on all windows that is made by the NRFC or something like that. National something Fenestration Council or whatever it is. I forget. If you look up fenestration, you'll probably find it quick online. I'll see if I can't remember it for next class, but it's not important. Okay? The most important thing to remember is when we're doing a load calc, remember, so far we've said if the wall doesn't go to the outside, it's not a wall, it's a partition, right? We'll repeat that soon, so if you didn't understand that, I'll repeat it, okay? But I won't repeat this much more. So the thing to remember is when we talk about windows and doors, A window is anything that is over 50% glass. A door or an opaque panel, right? An opaque door is one that is less than 50% glass. So if a door is less than 50% glass, it's a door, and you don't have to account for the window in it. If it is more than 50% glass, then it is a window, and we need to account for the glass in it. You really won't have, if it's like 50-50 and you call it a door or a window, you really won't have so much difference in the load calculation that you're going to break the bank, okay? Again, we're not trying to do rocket surgery. We're just trying to get a load calculation that's as close as possible to the actual load on the house. So we just round up or down. If it's less than 50% glass, it's a door, and it goes under doors. If it's more than 50% glass, it's a window, and it goes under windows. And we need to know what kind of glass is on that window. So the next most important thing on a window is the frame. Well, I don't know. Yeah, maybe. The rest of these are equally kind of important. We're just talking about the construction of a window, so we need to know these different things about the window. The next thing you need to know is the frame material. The frame material is the frame of the window itself. So when you buy a window, you buy it with whatever window frame it has, you know, whatever's holding the glass, not what the house is made of, right? Not what if the house is made of wood, that's not a wood frame window. It's a wood frame window if you get it and it's made out of wood and glass instead of metal and glass, all right? So the frame materials are metal with no break, metal with a break. Usually these days, if you're going to get metal, you'll get metal with a break. And if you know anything about duct or anything, you know that it's hard to see in this picture. I'm sure it's hard for you guys to see it, but basically you've got a little ridge in it. You've got a little break to try and help keep the air from moving in and out. So you got metal, no break, metal with a break, wood, clad wood, so wood with cladding on it, some kind of extra material over top, vinyl, insulated vinyl, reinforced vinyl, or insulated fiberglass. Typically, a newer window is going to be insulated vinyl or insulated fiberglass. You're generally safe with one of these options, and they're essentially the same. The numbers don't change a whole lot between the two. We'll talk about how you narrow these things down soon, but you do your best to look up the window and determine what it's made out of. You try and find out the manufacturer and all that stuff. If you are unsure and you have no idea, you should be able to figure out, is it vinyl, metal, or wood? And if it's vinyl, probably assume it's insulated vinyl. Okay? That's the most common one you're going to run across. It's pretty easy to tell, is that metal, wood, or vinyl? And if it's vinyl or fiberglass, assuming that it's insulated vinyl. You will generally be safe with that assumption if you don't know who made the window. Then whether or not you have any storm panes. A storm pane, we have to go clear. If you have a clear window, you can have a storm pane. The storm pane, I haven't seen these in a while. I swear I used to see them a lot more when I was a kid, but the storm pane is an actual another pane of glass, okay, on the outer side of the window. So where you would have an insect screen, instead of an insect screen, you actually have an extra window, a storm pane. That's a storm pane, okay? Then the next thing is whether or not the outer pane, so the pane on the outside of the window that goes to the outside, whether or not it's clear, with a low E coating. A low E coating is a low emissivity coating to keep the window from gaining as much heat, which is actually really common. If it's reflective, which is even better at reflecting heat, it's heat ABS or heat ABS low E. Heat ABS is going to actually be like a composite, like an ABS window, basically. Then whether or not the inner pane is clear or clear with a low E coating, whether the gap between the window is 1/4 inch or 1/2 inch, whether the glass is 1/8 inch thick or 1/4 inch thick, whether the gas in between the two panes is air or argon. Okay, so sometimes instead of filling the air between the two panes of glass, instead of having air in there, they'll fill it with argon because argon lets through less heat than air. Okay, so if it's filled with argon, it's a little bit more of an efficient window. And then you have different values for these low E's here and different values for the reflective performance. You'll have to pick those as well. I will tell you that if it is a newer house, typically what you're going to get, and I'm going to give you guys a table of all this stuff at one point because there's minimum energy standards that houses have to meet. So most houses are going to meet these minimum standards. But if it's a newer house and you're doing this, usually you're going to be operable window, insulated fiberglass, no storm pane. Outer pane will be, insulated vinyl, clear. Okay. Inner pane will be clear. Outer pane will be clear, low E. Glass thickness is 1/8 or 1/4. It depends. But generally just go 1/8. And then E 0.05 will usually get you to a U value that's close. Hopefully I got all those right. Pretty sure I did. Like I said, I'll give you guys a sheet, but the point is what you really will end up doing 99% of the time when you pick these windows is if you look over here, it'll give you results, what the SHGC is, what the U value without a storm pane is, what the MJ8 code is, and we'll learn about these codes next class or two. But what the codes are just helps us figure out what kind of window it is in the manual J. The MJ8 SHGC value without storm and the manual J8U value without storm. And the trick is that usually you're going to try and look up the window that it is and make all these values match the best you can. Okay? If all of these values match and all these things are picked right, you should be close enough. You know, if you come up with a 0.33 U value and the window says it's a 0.31 or a 0.32, you'll be close enough. But don't have a 0.5 U value window when it's supposed to be a 0.31. That's not close enough. Okay, you want to get within a couple points of what the correct U value is. And if you get within a couple points of the correct U value, you should be really close. All right, I know it seems like a ton of information, but the point is you just want your U values and your SHGC, which is your solar heat gain coefficient. You want those values to be as close as you can get them as correct, and you should be good. Again, if you can make sure anything, if there's anything you can make sure is right, try and get your windows right. Now, I know that was a lot, but there's actually more to windows. So, the other thing about windows that we have to make sure we get right is our defaults for our windows. With windows, it could also have blinds. It could also have insect screens, inside or outside. External sunscreens are kind of rare, but external sunscreens. The biggest thing next, though, is projections above it. So, can you guys see this little picture of a window right here? Let me see if it's popping up. Yep, it's popping up in OBS. So, you guys see this little picture of a window with an overhang on it?
Yep.
Okay, so the most important thing besides what the window's made out of is whether or not there's blinds inside or curtains or drapes or anything. Okay, so you have the options between different types of drapes, different types of roller shades, and different types of blinds. So drapes, if they're loose or dark, if they're medium or they're tight and they're white, roller shades if they're dark, translucent, or white, and Venetian blinds, whether they're open 45 degrees in dark, medium, or light in color, or if they're closed, dark, medium, or light in color. Here's the rule, okay? If you don't know what they're putting in the house as far as blinds or drapes, if you're not sure what they're doing, it's always blinds 45 degrees medium. That is your assumption. Your assumption is blinds 45 degrees medium, unless it's some kind of pretty window that you know they're not going to put any blinds on. You know, if like it's one of those architectural feature windows above the door, you know what I mean, where it's like some round window and you're never going to put blinds on that window, then it doesn't get blinds or anything, okay? But if it's a standard window in their living room or something like that, how many houses do you guys walk into where there's no blinds or any curtains or anything like that on the window? It's just an open window. I mean, every once in a while, but not that often. Most people have blinds on the windows, okay? So if you're not sure what it's going to get, you assume Venetian blinds at 45 degrees, medium in color, because that's kind of your most common one. Your next most common is drapes that are loose or medium. It's an important thing to remember if you're like walking through a house or something and people complain about how hot it is in there. If they have all their blinds wide open, if you close all those blinds halfway, you know what I mean? Let them all the way down and close them at 45 degrees. The amount of heat gain that you take out of that house is insane. Okay, it's a reasonable amount of heat gain that you get through those windows. Just by having blinds over them will mitigate. So we always assume blinds at 45 degrees, medium in color, unless you know better. If you know better, input the correct window covering and ask the owner, if you're doing a load calc, ask, are you going to put drapes or curtains or blinds? Okay, what kind are you going to put in? Because it makes a little bit of a difference and you will be more accurate that way. But again, if you're not sure, assume blinds at 45 degrees, or if you know it's a window that's just not going to get any type of window covering, then assume it has none. But don't make every window without any internal shade, because if you don't put any internal shade, then you're going to end up with an oversized system. Insect screen. If they've got an insect screen, what they have, whether it covers 50% of the window, so only the part that they can open, or whether it covers 100% of the window and it, you know, the insect screen goes across the whole window. You need to know if there's an insect screen because it affects the heat gain. And then if you have any type of projection that's going to shade the window from the sun. So on windows that face north, shading doesn't matter because we basically assume it's a shaded window because you get the least sun exposure on the north side of a house. Okay? So all your northern windows don't matter. But any window that faces east, west, or south, you have to account for any overhang above the window that will shade the window. So you need to input the correct values to determine how much of the window is shaded, how much it's being protected from the sun, and how much of it is directly in the sun. I will tell you, this is something we're not going to practice a lot, okay? It just takes too much work for us to get through this class and practice doing overhang shading. But if you're doing a load calculation in the real world and they have any type of overhangs over windows, so if the roof goes really far past the window and it overhangs the window more than like a foot or so, or they have any type of awnings over the windows or something like that, you need to account for that shading. The most common source of shading I end up inputting are things like balconies and decks, right? Balconies and decks usually end up shading windows a lot, and you want to account for those. But if there's any type of overhang, you need to account for that in the window, and you will have to input that information. Okay. So those are the default values. So we've just gotten through windows, and those are some important factors when considering a window. And we'll practice picking these out one by one. Basically, I'll give you what I'm going to end up doing is I'm going to end up saying, okay, I have a clear glass, double pane, operable window with a low E coating and maybe an E.1 value or something like that. I'll look through your guys' book and see how it's separated because it's a little different than the program. But then I'll make you find the window in the proper table. So the next class we'll talk about the tables, but I'm just trying to introduce you to each element and what we're looking for. Any questions on windows?
So far, so good.
All right. So with windows out of the way, your next and most important one is probably your ceiling. And that's only because of how much insulation there is in the ceiling, especially if you're under a ventilated attic. It has a huge effect on the second floor. I mean, massive, right? So your next most important one is probably a ceiling. The good thing is after you get past windows, you're not worried about overhangs or projections or blinds or any of that stuff. It all gets a lot easier once you get to ceilings, walls, and floors. So with ceilings, you need to know what type of ceiling you have. If you have a flat roof and ceiling, if you have a sloped roof and ceiling, if you have a ceiling that's underneath an attic, which is our most common, right? And that's pretty much it. There's ceiling partitions, but again, partitions are pretty rare. That's like for over garages and things like that. We'll talk about partitions last. So our most common is going to be a ceiling over an attic. And the important things to know are the roof material. So whether it's shingles, which is our most common, wooden shingles, tile slate or concrete, metal, tar and gravel, or a membrane. So obviously asphalt shingles are going to be your most common. Then after that would be probably metal, right? Copper metal roofing, something like that. And then wood shakers or wood shingles and tile and slat. But usually you'll be asphalt shingles, right? And then the ceiling finish, what's the ceiling made out of? Usually it's going to be half-inch gypsum board, which is drywall, right? Gypsum board is drywall. So anything, if it's drywall, that's what you pick, gypsum board. Or you might have something else, plaster board, fiber board, foam board, or something. But it's generally going to be your ceiling finish will be drywall, right? How much insulation is in the roof and how much insulation's in the ceiling? Usually you won't have any insulation in the roof. You might though. So if they have roof insulation, pick roof insulation, and that would be insulation right up against the roof. If you have ceiling insulation, you pick ceiling insulation, which is going to be insulation that's up in between the trusses of the ceiling, right on top of your drywall. So usually you're going to have ceiling insulation. Current code is R38. If the house was built more than about 5-10 years ago, before that it was R30. But if you're doing a newer house, the minimum that's supposed to be on that ceiling in a ventilated attic is R38. And then whether the attic is unvented, vented, or fan vented. And usually it's going to be vented or fan vented. it should be easy, right? Roofs are usually easy. The most important thing is to pick the right insulation. That has the largest effect on a roof, is the value of the insulation. And if you're unsure, I would generally pick R30. But an attic should be an easy thing to get up into the attic and find out how thick the insulation is. And depending on what type of insulation it is, you can get online and say, okay, what's the R value of 3-inch thick fiberglass bats? And then you can figure out the R value of the fiberglass insulation if it's not just written right on it. If it's that blow-in insulation, you need to know whether it's fiberglass or it is cellulose. And then you need to know how thick it is to determine what the R value is of that fiberglass or cellulose blow-in insulation. Those are the two most common you'll run into. After that, the next one is probably walls. So you need to know what the wall is made out of. And walls can get kind of complicated kind of fast, only because you're usually going to have more than one type of wall. Just because we have so many houses around here that have basements, you'll have the basement walls and then the walls on the upper floors. All right. So with the walls on an upper floor, you need to know what the exterior of the wall is made out of. It's usually going to be metal or brick, stucco or ephes. Usually, I think ephes is more common here than stucco, or it can be vinyl siding, wood siding, 8-inch brick or 4-inch brick, split logs, or a gypsum board. I'd say you're usually going to be picking 4-inch brick, vinyl siding, or ephes. And then maybe wood and split logs are your next most common. Vinyl siding is by far your most common, or metal siding. If it has any exterior board insulation, which is, I don't know, pretty rare, I think, but you do see it now and then. Sheathing, whether or not the vinyl is up against or whatever. What?
Are you referring to like buffalo board?
Buffalo board. What is buffalo board?
Yeah, it's like the fibery. It's like a fibery insulating board that they put on the outside of walls underneath the siding.
Yeah.
Is that what you're talking about?
Yeah, if you got any board, right? Any insulating board that's behind the siding or behind the siding but in front of your other insulation or sheathing, right? So if you look at this, if you've got insulation, you've got your sheathing, right? And then you'll have exterior board insulation right behind that, possibly right in front of, but usually right behind that. So I'm trying to look up buffalo board to see if I've seen it. Trying to find a picture of it on, yeah, something like that. I see a picture of it. Hardboard sheathing, maybe. Yeah, anything that's not the insulation like the fiberglass in the wall, but adds insulating value to the wall is going to be your exterior board insulation. Does that make sense? You just need to know the R value of whatever that is. Surprisingly, like, they don't ask you if these things are wrapped, and that always confused me. You would think because the wrap does make a difference on your infiltration, they'd ask you about that, but that's all accounted for in infiltration. So you don't need to know whether or not there's Tyvek wrap or anything like that when you build your wall. But it does help on infiltration later, which we're going to talk about a few classes from now. We're not talking about anything that has to do with air getting in the house yet. All right, so whether or not you have exterior board insulation, what your sheathing is, whether it's 3/8, 1/2 inch, or 5/8 wood or none. So if you're using, say, just an exterior board insulation but no sheathing, then you would pick it like that, right? So if there's no wood sheathing, then it's the exterior board insulation. Whether it's 2x4, 2x6 wood framed, or 2x4 or 2x6 metal frame, makes actually a pretty big difference, right? Yep, makes a pretty big difference. What the cavity insulation is, current code is R19. Before that, it's been, I want to say before that it was R13. I want to say it jumped right from 13 to 19, but I could be wrong there. But typically you're going to see R13 or 15, or you're going to see R19, one of those two. If it's an older house, what's that?
My wife says you're correct. She's a home builder and she's listening.
Okay. I'm glad I'm getting it right. It took me years to figure this crap out. But anyway, because I never really built homes a lot before I started doing load calcs. But that's a whole different thing. Okay, so then after that, whether your studs are 16 or 24 inches on center, it doesn't make much of a difference. But if you know it, put it in right. And then the interior finish is usually going to be 1/2-inch gypsum, right? Drywall. And then if you have an interior board insulation, I've never seen that. But if you do have an interior board insulation between your drywall and the wood, then you would put that in there. That's for a framed wall, so that assumes a wood or metal frame. If you have a masonry wall, so anything that is concrete or block, or no, basically just block and brick, a masonry wall, right? If you got blocks, we get to concrete walls. Masonry and concrete end up being really close though, so it's not a huge deal. If you're not 100% positive it's a concrete or block, you'll get pretty close as long as you know the approximate thickness. But anyway, your masonry walls, it's all the same thing, okay? Your masonry walls, whether it's metal, exterior is metal, brick, stucco, ephes, whatever. If you have any exterior board insulation between the block and the brick or whatever you have, whether or not you have sheathing, whether or not your structural wall is made out of sand and gravel block, tile and cinder block, lightweight block, or there's other options here, right? Concrete, your different concretes, and then aerated autoclaved concrete block. If you're not sure, then lightweight block is the way to go. All right. Structural wall thickness, how thick the concrete block or block wall is. Whether or not there's block insulation in the block, it's becoming a lot more common for them to fill the blocks with some type of perlite or something like that to insulate it. So if you have that, you need to put it in. Otherwise, no block insulation. If there's an interior framed wall on the other side of the block, so if it's not just like a furring strip and the drywall straight to it, then how big the frame wall is, how much insulation's in the cavity, and then what your interior finish is, usually 1/2-inch drywall, right? Then you have curtain walls. You won't see those very much. Miscellaneous walls, we're not talking about those. And then below grade walls and knee walls. Okay. Below grade walls are all your ones that are basements, right? So if on the other side of the wall, there is dirt. Okay, so if on the other side of the wall there's dirt and it's a below grade wall, it means there's no outside finish, right? You only have basically everything you had on a masonry wall, but you also have to pick the soil type. The soil type really makes no difference, okay? Pick heavy, dry, or light damp. This makes almost zero difference on your whole load calc. So we're pretty much always safe with heavy, dry, or light damp soil. Structural wall, whether it's block, brick, concrete, stone, ICF, which I can't remember what it stands for right now, but it's a engineered thing, right? Or plywood wood framing, you probably won't have that. Generally, it's concrete block or concrete, and again, It's not the biggest difference in the world when they're close to the same. The structural wall thickness, how deep it is below grade. So if the wall is only halfway below the ground and it's an 8-foot tall wall, you can pick 4 foot below grade. If it's all the way below the ground, it would be 8 foot below grade. What you want to do when you pick that is get the average. So, you know, if it starts at 2 foot below grade and ends at 6 foot below grade, you pick 4 foot below grade, so you've got an average. And you don't have to make a bunch of different walls with different numbers. You try and average out how much of the wall is below grade. So, you know, a lot of times what happens is you'll have a whole house and one side is completely below grade and one side's completely above grade. And you can just pick 4 foot below grade and your whole load will be close enough. You know what I mean? That's a pretty common scenario. And then board wrap insulation, what the interior framed wall is made out of, if you got an interior framed wall. And then the cavity insulation, right now it is R13, I think. I have to look. R11 or R13 on a below grade wall. They want some insulation there, but it's a pretty low requirement. And actually, isn't there another? Maybe not. Sometimes they'll give you another place to put that. It doesn't always have to be. Where's that? No, I guess you have to do cavity. I could have sworn, no, board wrap insulate ICFR value. I don't know. That should be right. And then knee walls, you're typically going to be using the knee wall for an attic. So if they've got a bonus room above an attic, or not above an attic, like if they used to have an attic and they make a bonus level out of the house, out of that area, and there's only part of a wall, and then it becomes the roof, okay? So when you've got like those little short, and you can kind of see the picture here, right? If you've got this wall that comes up only part of the way, that's a knee wall, because it's not a full height wall. It's a knee wall, right? And then it meets with the attic structure to become the roof. Okay, so this would be actually your ventilated attic, and this is just a roof ceiling combination basically above it. This is where you use knee walls. If you've got these little knee walls, it's extremely important to make sure you put them in right, because you lose a lot more heat in this situation than if you do with it just a normal ceiling under an attic. And these walls should be like R38 insulation, just like an attic would be, and sometimes they're not, okay? They just stuff these with R19 or something, and you basically end up with a huge heat loss right here, because you're basically a wall communicating with an attic. So this is what your knee walls are for. So you'll need to have the attic type here, and you'll need to have the roof insulation, the knee wall insulation, and then what the roof material is and what the interior finish is, and you build that out. So you see this a lot in like Arlington and stuff, is at least where I see it the most, where they're always renovating those old houses in Arlington or Falls Church. You'll have a lot of these knee walls. And those are walls. Floors. Probably the next most important is floors. You either have an exterior floor or an on below grade floor. Okay, an exterior floor, your most common is a crawl space, but anytime the floor communicates directly with the outside, like if you have an overhang on a house or something like that, you have an exterior floor. What it's framed out of, it's usually going to be a wood frame, right? What kind of insulation is in the cavity, how thick that is, usually R13 or 19. How thick the structure is, so how big your joists are, whether they're 2x6, 2x8, 2x10, or 2x12s. The exterior condition, whether it's open to the outside, or it's above a crawl space, or it's above a basement, or if it's above a garage. Those are your exterior conditions. Whether the floor is carpet, tile, hardwood, or vinyl. And then if the crawl space or basement has wall insulation in it, you put that in. And if there's any other exterior insulation, you can add that. If it's not an exterior crawl space, then it's a on or below grade. The thing about an on or below grade floor is that you only lose heat through the perimeter. So I know earlier that I was talking about if your floor is in the middle, you lose heat through the ground. Really, you don't lose heat through the ground, okay? And that's why I said we'll get to it here. But even though you kind of lose heat to the ground is such an average, even temperature, there's really no heat loss through the dirt. There's very little heat loss through the dirt, especially on a floor, okay? So on a slab on grade house, the heat loss is through the perimeter of the slab. So it's just like a wall in that you really only lose heat on the outside wall area of a slab on grade, whereas a crawl space, you lose it straight through the crawl space all the time, straight through the floor. So that's really the biggest difference when we go to doing calculations that you'll see, because when we input the area of a slab on grade, we'll actually input the perimeter instead of the floor area. And that's definitely next class. But anyway, just something to keep in mind. You actually need to put different numbers on these, but that'll make more sense after next class. What it's made out of, generally, what kind of soil it's on. Again, heavy, dry, or light damp is usually fine. Below grade depth, if the slab is below grade, then you'll have, if it's a basement, or whether it's an on grade, a slab on grade. If there's insulation around the edge of it, and this is pretty common now, they'll put insulation on the edge of the slab, going down the edge of the slab, so you lose less heat through the slab. If there's slab insulation on the interior or exterior of the slab, okay, sometimes you'll put exterior slab insulation, especially if they do radiant floors, radiant heat in the floors. You'll have full exterior slab insulation, but typically what you're going to have is edge insulation. And then the R value of that insulation, and then whether or not the floor there's a finish on it, or if it's carpet slash 80% carpet, 20% bare concrete, tile, hardwood, or vinyl. All those make a little bit of a difference. Those aren't super critical though. I mean, floor finish, the difference between no floor finish and a tile finish or a carpet finish is 0.046 or 0.045 to 0.047 in U value. Extremely small number. I wouldn't freak out about it too much, but if you do the floor finish right, again, the more accurate you are, the better. And the last thing that you need is doors. Doors are pretty easy. It's whether it's made out of wood or metal, and then there's overhead metal. The rest of these are like garage doors. But the most important ones are whether it's wood or metal, and whether it's solid or hollow wood, and whether it's got metal and what kind of insulation it has. If it's fiberglass, a honeycomb core, EPS core, or polyurethane. These are all just different insulations. Just get it as close as you can to right. Typically, it's going to be solid wood or hollow wood. But if you do get a metal door, it's good if you know if it's usually going to be a fiberglass or polyurethane insulation. If it's a honeycomb paper core, it's a really cheap metal door. Okay. And that's what we're going to work on first. We're going to work on, if we have a house, we're going to figure out how many square feet of walls we have We're going to figure out how many square feet of windows we have. We're going to figure out how many square feet of ceilings we have, how many square feet of floors we have, how many square feet of doors we have. Then we're going to look up all those different windows and doors. As a matter of fact, let's go back to this sheet for a minute. We're going to look up all these windows and doors, and we're going to say, okay, how much heat loss do I have through all my windows? Then we're going to say, okay, how much heat loss do I have through all my doors? Then we're going to say, how much heat loss do I have through all my ceilings? And so on and so forth. Because each one of those things lose heat at different rates. Again, the windows are the most important. And then after that, your attics, and then your walls, and then your floors, and your doors. Once we get through that, we can figure out everything else that's downstream. But that's the first step. The first step is going to be, how big is the house? How many square feet of all these things do I have? And how much heat do I lose through all these things on a design day? When it's 75 inside and 95 degrees outside, how many BTUs do I lose through all my windows? How many BTUs do I lose through all my doors, all my walls, all my floors? And then we just start adding all this stuff up. And that's how easy it is to size a system. So the next class is going to be mostly simple math. Any type of program that you can use to do this would be good. We're going to do this together. I'm going to show you using Bluebeam, but I'm going to try and give you guys some exercises that hopefully you can print out and maybe use a scale ruler on, or use some type of thing for, scaling drawings. You can do it with a tape measure, right? You can take a tape measure, and if I draw it at 1/4 inch per foot, you can measure it out using a tape measure and scale it. Hopefully we'll get there, but what we'll probably do first is I'll just draw it to scale and give you guys all the dimensions. And then I'll say, okay, how many square foot's the living room? How many square foot of wall is in the living room? Things like that. We're going to work on finding those numbers. Then we're going to work on finding the types of walls and stuff we have in our J8. And then we're going to work on the first step, which is the building of doing a load calc. After that, we'll work on the next step, which is how much air is getting in and out of the house, and what kind of internal loads do I have, and that looks like this. We get through all our windows and doors first. We probably won't do any exercises with skylights. We'll get through wood and metal doors in our walls, our ceilings, and our floors. Then after that, we get into infiltration and all that stuff, duct loss and gain, and all those happy things. But for now, it's going to be a lot of looking at drawings of houses. We'll try and do some relatively real examples without getting too crazy on how they're made. All right, that didn't go quite as I had pictured the class going. But that is your introduction to all the stuff that we're going to be looking at over the next lots of classes. It's going to be at least probably 6 to 8 classes on load calcs, if not 10 or 12. A lot of times we start running out of time when we get towards the end because it's a lot to cover. So I'm hoping I pushed to start us early enough that won't get too bad. But we'll see if we can cover all this stuff one by one. If you got any questions as you start looking at this stuff, I'm going to try and give you guys more exercises. Let me know and I'll help you through the little exercises we'll be doing. But try and make sure that you're getting it, because since we're not doing this in a classwork environment, I can't walk around to each one of y'all's desks and help you. Right? So it's going to be a little bit different. So I'm just going to kind of give this to you guys as like little quizzes and stuff after we start doing it. And you're going to have to fill out little assignments where we fill this sheet in. So again, when I post this on Google Classroom, you can probably simplify it a little bit, at least take out the partition walls and things like that. And then I'll expect you guys to fill out all the information on this sheet up to a block load. So you should be able to fill out this whole sheet by hand. It's not that bad. But we'll talk about that more next class. If you guys are good, I'm good. We'll work on building stuff next class, and then we'll go from there.
Awesome. Thank you very much. That was great.
All right. You have a good evening.
Thank you very much.
Yes, sir.
Sure. Good evening, everyone.
Night, Chris.
Night, bud.